Geometry Lesson 7-3. As we continue to talk about different forms of transformations, today we're going to specifically talk about rotation a little bit. So we have the center of rotation, which if you think about the word center of rotation, we know rotation is any time that an object is rotating around a fixed point, and that center is the fixed point. So the fixed point that a figure is turned about, on like a wheel, it would be the axle that it's all turning around. Anything would be turning around that. For us, in the solar system, we tend to rotate around the sun. We rotate as a planet around the center of the Earth itself rotates around its own axes. So there's quite a few different situations where you have a center of rotation. We also have the angle of rotation. Now this gets a little trickier for some people. Rays from the center of rotation to a point and its image. Now remember, the image is what happens after we transform. So originally you started with a point, and then it was rotated a certain amount of degrees to come to its image. So we might have a beginning point, which we could call B, and here's the center of rotation. And so from here to here is a ray, and then maybe we have its new rotation out here. We would say that this is the image after the transformation has taken place. So what happened was it rotated 90 degrees clockwise, as a clock would work. So it started here because this was the original point, but it became the image over here. So this is the angle of rotation. Alright, looking at that again, here's another shape that has the angle of rotation. Here we have a shape of an arrow. I'm calling it A with a little 1. That little 1 is read as prime. So this is the image. Alright? Over here we have A, which we're calling the pre-image. It hasn't been moved. It went from here over here, so we would say that this was 90 degrees counterclockwise, because it's going that direction. So we have the original image, the pre-image, and then we have the image we call A prime as it changes. So that can sometimes be tricky for people, is realizing how that works. Now, theorem of rotation means it is going to be an isometry. If you look at these shapes, nothing happened to the shape to alter its size, nothing happened to alter its shape. It's not twisted, deformed, enlarged, shrunken down. It's the exact same object, just in a different location. Rotated about this fixed point right here. So here we have a situation. Theorem 7.3 states that the measure of angle B to P to B double prime is equal to 2x. So let's look at the diagram. This is kind of a crazy diagram. This is our beginning image, and you can tell because it has no primes on it. Then the image was moved over here, probably by reflection. It looks like it was reflected over this vertical axis. So now we have A prime, B prime. So nothing's happened except that the distance from here to here is the same as the distance from here to here. So that's like reflection. But then the object was reflected again over this axis. And the angle of rotation that ends up becoming, a reflection and a reflection, is really just like a rotation. The angle that is between here gets doubled. That's what this formula is saying. So the measurement from, here's one part B, to the center of the rotation, to the B double prime, is going to be twice as big as whatever angle is between the lines that it was being reflected over. That's a tricky formula. Just remember, if you reflect once and you reflect twice, whatever angle forms these two lines we reflect over, we double it for the angle of rotation. So pretend that this angle right here was 40, then this would be an 80. If this were 90, this would be 180. It just doubles it. And our last actual definition is that rational symmetry, rotational, it shouldn't be rational, sorry. Rotational symmetry rotational symmetry. If a figure can be mapped onto itself by a rotation of 180 degrees or less. Mapped onto itself by 180 degrees or less. So here's an object. If we rotate this, now this is the top. If I go all the way down here to the bottom with my finger, that'll be a 180 degree rotation. But this shape actually maps onto itself before I make a complete 180 degrees. We go back, I draw a line right here. This is where that line for the top was. So now we rotate it. You can see rotational symmetry, it fits on itself. It'll rotate again another 60 degrees and it matches up with itself. Rotate again another 60 degrees and it matches up. So this has rotational symmetry because less than 180 degrees and it'll rotate on itself. All right, the Union Jack from England also has rotational symmetry. If I rotate this right here would be 90 degrees and it's still the exact same flag it was before. If I rotate another 90 degrees, which is 180, it still matches up because it can go 180 or less and be rotational symmetry. All right? These starfish have relatively rotational symmetry even though they're not perfect shapes. These crystals in the form of snowflakes also have rotational symmetry. They can be rotated less than 180 degrees and still map onto themselves. Right? This word, symmetry, has rotational symmetry. It rotates 180 degrees and becomes the same word, symmetry. So rotational symmetry has to do with being able to completely map onto its exact self with less than 180 degree rotation. The trickiest part is figuring out how much it's rotating. So you just got to think about your pre-image and the image and how much rotation actually took place to create